In the last lecture, we had initiated some discussions on the wave propagation solution of one dimensional continuous systems governed by the wave equation. And the reason why we are interested in this wave propagation solution is that we observed in our previous discussions that there are many systems in which we do not have eigen frequencies, we do not have eigen functions, for example systems with infinite dimensions or the spatial dimension infinity. So, infinite system so to say. So, for such systems and also systems with special conditions, for example a bar with boundary damping, we have observed that for such systems we did not have eigen frequencies or eigen values. So, for such systems we need to study this wave propagation solution. There are other examples that we have observed and discussed in our previous lectures. For example, we would like to understand how a transient solution evolves. For example, we have seen that for the initial value problem with velocity initial condition, we have a propagating front which interacts with the boundary of the system, and then there is reflection, and there can be other things that we are will discuss in the course of these lectures. And then we are also interested in the wave propagation solution because wave propagation is a very nice way of evaluating material properties or characterizing materials in terms of, for example, wave speeds, in terms of presence of discontinuities or defects. So, from all these considerations we are motivated to study this wave propagation solution. Now, in the previous lecture we have seen that for a system, for this for a system governed by the wave equation, there are no boundary conditions because the system is of infinite size. So, the spatial dimensions are infinity. When the disturbance is, we can consider, we can drop the boundary conditions even in cases where the disturbance has not reached the boundary, and we would like to study the transients in the system. So, for that such situations also the system is governed by the wave equation and there are no boundary conditions, we do not consider the boundaries. Then we observed that a general solution of the wave equation can be which is known as the Alembert solution. Now, so the Alembert solution tells us that the solution of the general solution of this wave equation in terms of positive travelling wave and a negative travelling wave. And as we will see that this solution will allow us to understand the transient behavior of systems that are governed by this wave equation. Now, today what we are going to look at is, now given this system and now suppose we are given some initial conditions. Suppose the initial conditions are specified like this, that the system is given an initial shape defined like this, and the initial velocity distributed in this form, where so the domain of this problem from minus infinity to plus infinity. So, this is therefore the statement of our initial value problem for our system. So, let us then substitute this solution form, the general solution form, in the initial condition expressions, and we obtain from here, and from here we have so we have these two conditions. Now, let us first look at this velocity condition. So, if we integrate this velocity condition, what we obtain is so we are integrating over from x 0 to x, and I will put this 1 minus 1 over c on the right hand side. Now, I can integrate this to write so f evaluated at x 0, so this is what we are going to get. Now, this along with what we have obtained here. So, these are the two equations we can solve simultaneously to determine f x and g x. So, for example, if you just add these two, we obtain f x, and similarly if I subtract the first from the second, so we have these expressions of f and g. Therefore, we can now write the general solution. So, we have to substitute in place of x here x minus c t, here we have to substitute x plus c t, and we have to add these two. So, these are independent of x. So, when we add these two, they will get cancelled. So, what we will obtain, so let me write this W 0 term and we have these integrals Now, therefore, I can write this as, you see, if you look at these two integrals, then the limits are from x 0 to x minus c t with a negative sign, and from here it is x 0 to x plus c t with a positive sign, and the integrands are the same. So, I can combine these two integrals and write them as so here I reverse the order. So, this becomes plus x minus c t to x 0, and this is x 0 to x plus c t. So, this becomes x minus c t to x plus c t. So, this is the Alembert solution for the initial value problem. So, given the initial shape of the system or the configuration of the system and the initial velocity distribution, using this solution we can determine the solution at any space point at any time instant. So, this solution is an exact solution. In that, what we have been discussing previously, we were for normal strings with fixed boundaries, we were expanding in terms of the eigenfunctions, and there are infinitely many eigenfunctions, but when we do the computations we have to somewhere truncate, because we either we sum up the series somehow, but if we cannot sum up the series and have a closed form solution, then we must truncate the series somewhere. Now, once we truncate the series, what we get are the approximate solutions of the wave equation, which we have already seen in the previous lectures. But this solution is in that way exact, because we have it the solution in terms of the shapes of the initial configuration and initial velocity distribution over the string. The next thing to observe is the solution is dependent on the velocity distribution. Since this is an integral, so the initial velocity distribution is integrated from x minus c t to x plus c t. So, therefore, the velocity distribution in this range is of importance for the solution. So, let us understand this in the space time diagram, what we have discussed in the previous lecture. So, let us consider the space time diagram. We have seen in the last lecture that the solution at any point x t, let us say, so it is a summation of a positive travelling wave and a negative travelling wave. Now, in the space time diagram, the positive travelling wave moves along the characteristics, the positive characteristics of the wave. So, let us say so this when the time has progressed from 0 to t. So, the equation of this blue line is given by this, where this is, let us say, x 0, and for this green line so this is, let us say, x 1. Now, what we so therefore, this this x 0 point is nothing but x minus c t. So, the slope of this line is plus c and the slope of this line is minus c. So, this x 0 is actually x minus c t and this is x plus c t. So, solution, as you can see in this solution form, it depends on this whole interval, the integral of the velocity distribution over this interval. This is called domain of dependence. Of the solution. So, the solution at any space point x and at any time t is dependent on the distribution of initial conditions in this domain. Now, if the initial velocity is 0, for example, if the initial velocity is 0, then of course, this integral vanishes. So, then we find that the solution here is dependent only on the displacements at these 2 points at time t equal to 0. That gets summed up here as we see here. So, let us consider these two cases separately now. So, let us consider the first case with 0 initial velocity. So, which means that this is 0 for all x. In that case, if you look at the solution, then so this is what is happening. Now to understand this, let me rewrite this. So, whatever is the initial configuration or shape of the system, we half it. One half will travel in the positive direction, the other half will travel in the negative direction. So, let us see this. Suppose the initial shape is given like this. So, this is so at time t equal to 0, this is the shape of, or this is the configuration of the system. Suppose you consider this to be a string, let us say. Suppose this is a string. So, the shape of the string is like this. Now, at a later time, so this initial shape, let me first half it. So, this is one half of this function. Now, so one half will travel in the positive direction and one half will travel in the negative direction. So, let me try to so this has travelled in the negative direction and one half will travel so the net displacement of the string is given by the summation of these two. So, this is going to be so here there is a kink. Now, as time progresses further, so these two pulses have separated out. So, the net solution looks like this. So, this is suppose this is t equal to t 1 and this is t equal to t 2, then this pulse is the solution is this solution and the other one is the negative travelling pulse. So, that is how the system is going to evolve as time progresses. So, given this initial shape, so one half of that configuration or the shape of that function will move to the right or to the positive direction, the other half will move to the left, and this is how it is going to look like. But this usually giving an initial shape is more difficult in practical situations. What we can give quite easily is initial velocity condition. This is very important from practical considerations as well. Now, we have seen in one of the previous discussions that an initial value problem, let us say so, an initial value problem of this form can be equivalently represented. So, this the governing equation, there are no boundary conditions as we are considering in finite systems. So, these two systems are equivalent. So, here we have forcing in place of initial conditions. So, a system with initial conditions can be looked at as a system with forcing in this form, where this delta t is the Dirac delta function at t equal to 0 and delta dot is the derivative of the Dirac delta function, which has certain properties that we are going to discuss. Now, when we have only initial velocity condition, there is no initial displacement. So, our equation of motion is given by this. So, this is an impulse applied at time t equal to 0. With the distribution given by V 0 of x. Now, for very special in very special situations, for example, when we strike the key of a piano, or we strike the string of a santoor, for example, with the hammer or the mallet, then what we are giving is, we are giving an impulsive force at a particular location. So, for this distribution function V 0 x, if it happens to be a Dirac delta function, then we are representing such situations like striking the hammer of a piano or the hammer of a santoor on the string. So, this by various choices you can produce or this model. So, I mean this equation governs the dynamics of, let us say, a piano string or a santoor string. So, we I mean this system is important from practical considerations. So, let us look at the initial velocity condition. So, what we now have is, this is 0 and V 0 x is something specified. Now, let us look at the situation that I just now discussed. Let us say the initial condition initial velocity distribution is a Dirac delta function applied at x equal to a. In that case, you see this, if you look at the solution, let us look at the solution once again. So, these are 0, this is the Dirac delta function. Let me write down. So, if you substitute this expression in here, then you will find that so you have to perform this integral. You have to perform this integral. Now, when this is a Dirac delta function, then the integral of the Dirac delta function is the Heaviside step function. So, if you take this, so this is the Heaviside step function. So, using this Heaviside step and substituting it here, you will find that the solution reduces to so if you substitute this in here, so this h of at x 0 it cancels off, what remains is h at x plus c t minus h minus x minus c t and divided by 2 c. Now, this let me once again draw the solution. So, initial shape of let us say the string is 0. So, there is no displacement, and I have given this step let us say at x equal to a. So, this actually is there is a minus a because I have given the impulse at x equal to a. So, this can be represented. So, let us say this is x equal to a. So, it is the sum of two Heaviside step functions, one is this one, the other is minus. So, this is the lower one is this solution, and so this is and this is 1 over. So, the summation of these two is 0. Now, as time progresses, this is going to move in the negative direction and this is going to move in the positive direction. If that is the situation, then therefore, the total solution is the sum of these two. So, what we have is a rectangular pulse spreading like this. Now, instead of an impulse, because impulse is little difficult to produce exactly, if you produce a distribution, then that pulse shape is going to change, and this we have seen as an example of a string with initial velocity distribution in one of the previous lectures. So, what happens is there is a hump which is spreading, it is spreading out in both directions, it is expanding, the hump is expanding. So, you can understand from this simple example that here there is a rectangular pulse which is expanding. So, this and you can see that as time progresses, the string is going to take up a constant deflection, which is given by the height of this. So, this happens to be 1 over 2 c. So, this tells us about what happens when we have an initial velocity condition. Now, we can solve this same problem using Fourier transform. Now, when we have systems of infinite extent, Fourier transform is a very powerful technique which can be used to solve initial value problems. So, let us look briefly how this is done. One thing we assume when we consider Fourier transform for initial value problem is that the disturbance, whatever initial conditions are given, is 0 at infinity. This is this assumption is made to ensure that the Fourier transform exists. So, we must satisfy the condition of existence of the Fourier transform, otherwise this method would fail. So, with this assumption, we must have square integrable functions. So, disturbance is such that the initial conditions is such that its Fourier transform exists, and we are looking at finite time, so that the disturbance has not spread out from minus infinity to plus infinity. So, this is an assumption that we make in this approach. So, our equation of motion is given like this. There are initial conditions, we define the Fourier transform So, this is the definition of the Fourier transform. And we must also look at the inverse Fourier transform, or what is known as the Fourier integral. So, this is known as the Fourier integral. Now, what we do is we take the Fourier transform of the equation of motion. So, if we do that, and of course, also of the initial conditions. So, if you take the Fourier transform and simplify, so this and along with that we have now we know the general solution of an equation of this form. So, this is the general solution. Now, we use the conditions, the initial conditions, and we find that a plus b must be equal to w 0 of k and a minus b must be equal to and from here we therefore can solve. A and b, and once we have solved for a and b, our solution can be written like this, which can be easily obtained by substituting this in the general solution and simplifying. Now, once we have this, we use the inverse Fourier transform or the Fourier integral to write down once you substitute this here and perform the Fourier integral, which is straightforward. So, you can get to the solution which we had obtained before. So, you substitute this here and use the definitions of this w 0 tilde. So, when you put this in the inverse Fourier, then you will get w 0 and this has to be evaluated at x plus c t and x minus c t. So, this is more or less straightforward and you can obtain this solution. So, to summarize what we have looked at in today's lecture, we started with the initial value problem. We have looked at some examples of initial conditions and we have obtained the corresponding solution using the Alembert solution for the wave equation in terms of propagating waves, and we have understood how for example, given an initial displacement condition or an initial velocity condition, how the solution, we can understand the solution, or how we can see the evolution of the solution as time progresses, and these are in terms of propagating fronts. So, we have seen, for example, in case of initial velocity condition, which is more practical, for example, in pianos or santur, where we give impulsive loading on the string, how the disturbance front propagates as time progresses. And towards the end, we have briefly looked at the Fourier transform solution of the initial value problem, and obtained the same solution as we have obtained earlier in this lecture. So, with that we conclude this lecture.